Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is divide and conquer strategy. Divide and conquer. So in today's session we'll see the introduction, what is about this divided and conquer strategy, and what are the different applications which will follow this strategy divide and conquer in order to solve the problem. So in our first sessions we have seen there are different strategies like divide and conquer, dynamic programming, greedy method, etc. in order to solve any problem. So the main goal is to achieve the optimal solution, right? The better solution. So one of the strategies divide and conquer, and so here there will be three parts: divide, conquer and combine. So for the first part is a divide part, so where the complete problem can be decomposed into multiple sub problems. So first the problem will be divided into multiple sub problems. So that will be done in this divide part. Okay, so the problem is decomposed to multiple sub problems. The second part is a conquer. So as the name itself indicates, it's a conquer. So conquer means applying some recursive calls or recursive procedure to solve each and every sub problem, right? So the second part, conquer, so providing solution or finding the solution for every sub problem. So finding solution for every sub problem. And there is also a third part which is called a combine. So after finding the solution for all the sub problems, the next part will be the combine. So we have to combine the solutions of all sub problems to get the main solution. So the third part will be combine. So the name itself indicates combines means so joining or integrating the solutions of all sub problems. So combining solutions of all sub problems. Right? So these are the three steps involved in this divide and conquer. Usually some materials or some textbooks or some online information will be having as a D and C, right? So it will be represented as a D and C, divide and conquer, right? So and the applications, what are the different applications that follows this particular divide and conquer? So the main applications which follows this divide and conquer are binary search, so where the complete element should be in a sorted order, so that we have to find the middle element and we are trying to compare the search element with the middle element, so that we are deciding whether the search element is available at the left part of the middle element or the right part of the middle element, right? So the search space in the second iteration, the search space will be reduced to half. So in the second iteration we will follow the search space from either first to middle or middle to last. So that approach will follow this divide and conquer. So first we are dividing the problem, and again we are applying the same procedure, and based upon the result we are proceeding with the further division, or we are combining the solutions. So first one will be the binary search. Next, Quick sort. So as we know that sort means arranging the elements in a ascending order or either descending order. Usually the elements will be arranged in a ascending order. So here also we will be having a lot of elements. So usually that will be stored in an array. So we have to consider a pivot element, and based upon the pivot element, all the elements that are less than the pivot should be arranged towards the left side, and all the elements greater than the pivot elements will be arranged towards the right side. Now the complete array is divided into two halves, left half and right half. And again from the left half, again we have to select the pivot element, and again based upon the pivot we are arranging two sub arrays. And coming to the rightmost array, again we are dividing the rightmost array based upon the pivot, two sub arrays. So this is again the process which follows the divide and conquer. So dividing the problem and providing the solution, finding the solution, and again combining all the solutions. So quicksort is also an application which follows this divide and conquer methodology. And merge sort. So this is also one sorting technique. So where here also the elements will be arranged in a sorted order. So here first of all we have to divide the complete array into two halves, and further again this left sub array and right sub array will be further divided into again two halves until it reaches to the two elements, right? So then again the process will be from bottom to top. So for every sub problem, for every sub array, we have to arrange the elements, we have to compare the elements, and we have to arrange the elements in a sorted order, and again we have to merge two arrays, and again we have to compare, and we have to apply the sorting technique, and again we have to apply we have to combine both the arrays. So merge sort means again first we are going to divide the complete array into sub arrays, and again we are just combining all the merged elements, all the sorted elements. So merge sort is also one application that follows this divide and conquer. So don't worry about it. So one by one we'll solve each and everything. So we'll see how we have to apply the divide and conquer. And one thing you have to remember, either you are using the binary search or a quick sort or a merge sort. So two things are common. So one is formula. So formula means at what point we have to divide the complete problem into sub problems. So according to which condition we have to divide it. Okay, so that is a formula, because in binary search we are finding the middle element, and based upon the middle element we are comparing with the search element, and then we are dividing. Coming to the quick sort, we are finding the pivot element, and based upon the pivot element we are dividing. And coming to the merge sort, this is also we are finding the middle element, and we are dividing this complete array into sub arrays. So we required some formula to divide the problem into sub problems. And the next one, stop case. So stop case means how far we have to divide the problem into sub problems. So at particular time we have to stop that division. So that is most important, stop case, right? So identifying the stop case or base condition is somewhat difficult. So that may be one disadvantage of divide and conquer. And also not all applications will follow this divide and conquer, and this will be not suitable for all the applications to get the optimal solution. So right, so you can see these are the few applications. So I'll draw the simple diagrammatic representation about these three parts, right? So you can see first complete problem. So one advantage is complex problems can be easily solved by using this divide and conquer. So for example, this is a problem. This is a problem. So this is again divided into two subproblems. Two subproblems, right? So subproblem 1 and subproblem 2. This is a complete problem, right? So based upon the formula and based upon the stop case, again this subproblem can be divided into further, right? So for example, again this is divided. So problem 1, so problem 2, and again so problem 1. So this process will be keeps on moving, right? It keeps on moving. So once it was done, now finding the solution, and here also finding the solution, and here also we'll be having solution, and here also we'll be having solution. Now division is completed and conquer is completed, right? So up to here, that is a divide part, and up to here this is a conquer part, that means finding the solutions, and after that we have to combine both the solution, right? So this is a combined part. So again here we have to combine both the solutions, and later again we have to combine complete solution, right? So this part is nothing but combine. So 3 parts: divide, conquer and combine. Dividing the problem into subproblems, right? So this is a part, and this is a conquer part, and this will be the combine part. Okay, this is completely the combined part. So identifying the problem, subproblem, and applying the same procedure in order to find the solution, finding the solution and combine the solution. So finally we'll get the complete solution for this particular problem. Okay, so the same approach will be applied for, we have seen the applications merge sort, quick sort, or towers of Hanai problem, and as well as the binary search. Okay, multiplication methods, finding the minimum and maximum elements. We can also use the same strategy in order to find the maximum and minimum elements. Right? So hope you understood the complete introduction. What is this divide and conquer strategy? So to get the optimal solution. So let's stop here, and in our further sessions we'll see each and every application that follows this divide and conquer and how we can get the optimal solutions. Right? So hope you understood this one. Let's stop here. So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms. So in our previous sessions we have started the divide and conquer strategy. So where we have seen the 3 parts. So one is dividing the problem into different subproblems, and then conquering, that means solving each subproblem recursively, and finally combining, so where all the solutions of all the subproblems will be combined to get the final solution. So we have seen a few applications like finding the minimum and maximum element, merge sort, quick sort, binary search, etc., etc. So in this session we'll see one application, that is finding the minimum and maximum element from a given array using this divide and conquer methodology, right? So usually this is called as a min and max algorithm. So the problem statement is to find the minimum element and a maximum element from the given array, right? So using this divide and conquer. So absence of this divide and conquer, so how can we find the minimum and maximum value? So for example, array is having some 5 elements, and let us assume these elements are not in a sorted order. Okay, so not in sorted order. So what happens? So in order to find the minimum element, how many comparisons we require? So we have to compare the first element with all the other elements, whether it is a minimum value or a maximum value. If it is a maximum value, we have to swap, right? So finally we require 4 comparisons. 4 comparisons, right? So similarly, in order to find the maximum also, it requires 4 comparisons. 4 comparisons. And if array is having some n elements, so in order to find the minimum value, it requires n minus 1 comparisons. And for finding the maximum value also requires some n minus 1 comparisons. So finally, if you want to find minimum and maximum in the same algorithm, it requires n minus 1 plus n minus 1. That implies 2n minus 2 comparisons are required. So if the elements are not in a sorted order, right? If the elements are not in a sorted order, so in order to find this minimum and maximum elements, we require some 2n minus 2 comparisons. So obviously the time complexity will be order of n, because we need to avoid the constants, right? So the time complexity will be order of n itself. But practically, how many comparisons were we required? So 2n minus 1 in the absence of divide and conquer. This is a normal method, right? So remember this one. So 2n minus 2 comparisons. Okay, conventional model, or we can call it as a linear model. Now we'll see how many comparisons we required if we solve the same problem by using a divide and conquer, right? So that means dividing the problem into sub-problems and solving each sub-problem using recursion, and then combining the solutions of all sub-problems, right? Now let us see one by one. In this session, I'll mainly focus on example. First, we'll see the example how we can find the minimum and maximum element from the unsorted array using divide and conquer, and then we'll see the algorithm. We'll write the algorithm, okay, how we can based upon the example, and then we'll find the time complexity, right? So obviously the time complexity will be order of n, that's a no doubt. But we'll see how many comparisons it requires if we solve with the divide and conquer. Okay, so in linear we are having some 2n minus 2. Now we'll see the comparisons, right? So you will see in terms of comparisons, how many comparisons it requires, right? So I'm going to cover all these 3 in today's session, right? Yeah. Let's start with an example. So we'll take a few elements, so random elements, so the elements are not in a sorted order, right? So I'll take some 40, 60, 50, 30, 20, and let us take it 10, right? So there are a few elements, so usually 6 elements, we are considering the 6 elements. Now what we have to do, we have to divide it into sub-problems. For division, here we are taking the formula as a middle element, right? So 2 things we have to remember. In our previous session we have discussed about that one. 2 things, that is, which criteria we need to consider to divide the complete problem, and the second one, the stop condition. So at which position we have to stop the recursion. That means we have to stop the division, right? So the formula is a middle value. We need to find the middle value, right? So let us consider it as a low, and let us consider it as a high, and let us consider the index values 0, 1, 2, 3, 4 and 5. So this is an array. Okay, this is an array and these are the index values, and low is initialized to 0 and high is initialized to 5. right? That means n minus 1 if n is equal to 6. Now find out the middle value. So I'll write here middle is equal to, so middle value how we can get, low plus high divided by 2. So here how much we get, 0 plus 5 divided by 2. How much we get, 5 divided by 2. So we need to consider only integer. So it will be 2. We need to consider only integer. So we need to divide the complete problem into 2 sub arrays. That means complete array into 2 sub arrays. So the first array will be from 0 to 2. That means low to mid. And the second array, what is the second array? Obviously the second array will be from 3 to 5. Usually we call it as a mid plus 1 to high. So based upon the middle value, we are going to divide the complete array into 2 sub arrays. Now consider, so let it be, so 40, 60, 50. So 40, 60 and 50. And here also the second array consists of 3 elements. So what are the 3 elements? 30, 20, 10. 30, 20, 10. So again we have to repeat the same process. That means recursion should be done. Recursively we have to solve each and every problem. So we are having the complete problem, and after first step we are having 2 sub problems. And now from these 2 sub problems, again each sub problem should be solved by using the same procedure. That means a recursion, right? That we call it as a conquer. So again here let it be 0, 1 and 2, and here also 0, 1 and 2, and let it be here a low value, and this is a high value, and again here is a low value, and this is a high value. So here mid is equal to low plus high by 2, 0 plus 2 by 2, and here also mid is equal to 0 plus 2 by 2. So how much we get? 2 by 2, it's 1, and here also we get 1. So we are applying the same procedure. And based upon this we are again dividing the same array into different parts. So again this will be divided from 0 to mid, that means low to mid, and mid plus 1 to high. See, so I am taking low to mid, that means 40 and 60, and mid plus 1 to high. So obviously mid plus 1 and high both are equal, so we are having only one element, 50. And here also the same procedure. So what happens? Again 2 elements, it was divided into 2 elements, 30 and 20, and again the same single element which is a 10. So complete problem, sub problem, and again sub problem. So we need to stop here, because if the total number of elements are equal to 2, then only one comparison is required. So we can compare 40 and 60 so that we can get the minimum and maximum value, right? So among these 2 values we can simply say that with one comparison we can say which one is the minimum value and which one will be the maximum value. And if the array consists of only one element, so then the minimum and maximum value will be the same. So we need to stop this recursion whenever the division, after division, if the count is equal to 2, okay, we can stop it. So stop procedure. So I'll write here stop. When we have to stop condition. So whenever it becomes 2 power I is equal to 2. Okay, so or simply we can say it as a k. So anything we can represent simply 2 2 power k. Means here we have divided into n2, okay, and further we have divided into 2. So that means here we can write it as n by 2 and here we can write it as n by 4, because n by 2 again we are dividing it into 2 halves. Okay, so we have to repeat the same process: n by 2, n by 4, n by 8, n by 16, and this process will be repeated until that equal to 2. Okay, this is a stop condition. Whenever it becomes 2, then we have to stop it. Now we are stopping here, right? Now directly we need to compare these two values. So compare these two values and we can find what is a minimum and what is a maximum. So here you can say minimum is equal to 40, maximum is equal to 60. And here we are having only one element, so the minimum value and maximum value will be the same. So a minimum is equal to 50, maximum is equal to 50. And apply the same process on the second half also. So here also the minimum value will be 20. So we need to compare. Okay, we need to compare whether 30 is greater or 20 is greater. So obviously 20 is greater, right? Only one comparison is required. And a maximum is equal to 30. And here only one element, so minimum is equal to 10 and maximum is equal to 10. Right? So two conditions we have done. If the number of elements are 1, then there is no comparison. So the minimum element and maximum element will be the same element. And the second condition, if the number of elements are 2, it requires one comparison. And based upon that one comparison, we can consider or we can assume what is the minimum value and what is the maximum value. Now we have to, we solved their subproblems. So this subproblem has been solved. So we got minimum value and maximum value. And this subproblem also solved. We got minimum and maximum. This subproblem we got a solution, minimum and maximum. This subproblem we got a solution, minimum and maximum. Now the third part should be started. So what is the third part? So third part is combining. Combining both the solutions, all the solutions. Okay. So first we have to combine these two solutions. So combining these two solutions, we have to compare this minimum with this minimum. So 40 and 50. So what is the minimum value here? So here minimum value from this one and this one, the minimum value will be 40. And similarly maximum should also be compared, 60 and 50. Which one will be the maximum? So obviously 60. So after combining these two solutions, we got a solution minimum 40 and maximum 60. And apply the same procedure for these two halves. So minimum 20 and minimum 10. When we compare these two things, the minimum value will be 10. And compare these two things, maximum 30 and maximum 10. So it will be a maximum 30. So after combining these two solutions, we got a solution min is equal to 10, the max is equal to 30. Now we have to compare these two things. Okay, these two things, and this one and this one. So when we compare this one, minimum 40 and minimum 10. So compare the minimum value from both the solutions. Compare the maximum value from both the solutions. So from these two solutions, the minimum value will be 40 and 10, and maximum value will be 60 and 30, 60. So this is the final solution. So from the given elements, you can observe which one is the minimum element, that is a 10, and which one is the maximum element, that is 60. So we have applied the divide and conquer method. So we have divided the complete problem into subproblems, and then we have solved each subproblem, and then we have combined the solutions of all subproblems, right? So this is the procedure and this is the example. I think everyone understood this example. Now based upon this example, we will write the algorithm. Okay, so hope everyone understood this example, right? So we'll write the algorithm for this one. So I don't want to erase all these things because further we'll use the thing, right? See, algorithm or pseudocode, whatever it may be, we can write. So I'll give the name it as a min max. The algorithm name is min max. So it will take a few arguments like low, high, min and a max. So I take this one. Now what we have to do? So first we have to check whether the array elements are equal to 1 or 2. So if low is equal to high, so we have to initialize low with a 0 and high with n minus 1. Okay, if it is having some n elements, we have to initialize high with the n minus 1. So after that, if we get a low is equal to high, that means only one value is there. If the array consists of only one value, then obviously what happens here, we have seen both the min and maximum will be the same, right? So what we have to do, so the minimum is equal to some array of low or high, anything is common, right? Similarly, maximum is equal to a of high or low, whatever it may be. You can write anything because both are equal, right? Yes. Now the second condition, if it is having two elements, okay, the same thing which we happens here in the last step. Okay, so we got one array with two elements, one array with one element. So what happens here? Else if low is equal to high minus 1, that means if it is having a two elements, okay, if it is having two elements, what we have to do? We have to compare. So what we have to compare? If a of low is less than a of high, so we are comparing both the things. Okay, if only two elements, we are comparing both the elements. So if a is low is less than a of high, we can simply say minimum is equal to a of low and the maximum will be a of high, obviously. And else that means a of low is less than greater than a of high. That means if the first element is greater than the second element, obviously the minimum element will be a of high, maximum element will be a of low, right? So this is the first condition when the number of elements are 1, and this is the second condition when the number of elements are 2. Now when the elements are greater than 2, what happens? Again we have to divide. And we have to apply the same process. So else part, and what we have to do? We have to calculate the middle element. So middle element is equal to low plus high divided by 2. Low plus high divided by 2. And then we have to divide two arrays. What is the two arrays? The first one, the name is min max, and we have to apply the same procedure. So min max of low. What is the high value here? So obviously it will be mid, and we'll take it as a min 1 and max 1. And second array, this is the first array. Second array, min max, what we have to consider? Mid plus 1 to high, and from here we will going to get minimum 2 and maximum 2. So after completion of these things, we will get only minimum and maximum, both the cases, min 1, max 1, min 2 and max 2. Now we have to compare these two things. So after that we have to compare if min 1 is less than min 2. So min 1 is less than min 2. So what we have to consider, minimum value is equal to, okay, min 1, else min 1 is equal to, min is equal to min 1, else min is equal to min 2. Okay, so if minimum 1 is less than minimum 2, so that means in the last step, if both we have to compare both the minimum values, right? And the same thing should be applied for maximum also. If max 1 is greater than max 2, what happens? So max will be max 1, else max will be max 2. So this is the algorithm for finding the minimum and maximum values, from the single array, unsorted array, by using the divide and conquer method. So hope you understood. What we have done in the example, the same thing we have written in algorithm, right? So first condition, this is n is equal to 1 element, n is equal to 2 elements, and this part is n is greater than 2 elements. This is n is greater than 2 elements, right? So 3 conditions, we are writing these 3 conditions, and this part will be repeated until n by 2 power k is equal to 2, right? So hope you understood. Now we'll see how many comparisons we require if we apply this kind of algorithm, okay, divide and conquer algorithm. So by using the linear algorithm, so linear method, the time complexity or the number of comparisons will be 2n minus 2, and now we'll see the time complexity, that means the number of comparisons for this particular algorithm. See, if there are n elements, so we are dividing it to n by 2, n by 2 and n by 2, and again this is divided into n by 2 and n by 2. This is divided by n by 2, n by 2. Further it is divided by n by 2, n by 2. Okay, and this process will be repeated. And when we have to stop? We have to stop whenever n by 2 power k is equal to 2. That means after division, if the number of elements are 2, then we have to stop the division operation. Now, see the complexity or the comparisons, whatever it may be, we'll write here T of n is equal to 0. That means 0 comparisons if n is equal to 1. That means only one element is there, 0 comparisons will be there. Then it will be 1 if n is equal to 2 elements. If n is equal, if array is having 2 elements, only 1 comparison is required. And if it is, right. So if it is greater than 2, then what we are doing, we are dividing the complete array into 2 halves. So n by 2, okay, plus n by 2, right, plus 1 plus 1, and this is if n is greater than 2, and this is the time complexity of first half plus time complexity of second half, and this is for divide, and this is for combine the results. So if the number of elements are greater than 2, then it will be n by 2 plus n by 2, so plus 1 plus 1. So this we can write it as 2t n by 2 plus 2. So like this we can write it. Okay, if n is, if the elements are greater than 2, then the complexity will be this one. So we have to divide the two halves, and again further we have to divide the two halves. Then we can see t of n by 2 will be, so apply the same. This is for t of n. Now t of n by 2, then it will be 2 into 2t of n by 2 divided by 2 plus 2. Okay, so this is this one plus 2. Okay, we are just substituting n by 2 here. Okay, now this happens with, so 4t, and this will be n by 4 plus 2 2s are 4 plus 2. Similarly, again divide it into n by 2. Again divided into n by 2. So again we'll apply the n by 2 here itself. Okay, or simply we can go with the n by 4 also. Okay, if it is n by 4, apply the same thing. Okay, so let us take further, it is divided. So 4 into 2t of n by 4 divided by 2. So further we are dividing. Okay, so plus 2, and write down all those things. 4 plus 2. So if you solve this one, it will be 8t into n by 8 plus 8 plus 4 plus 2. Right? So, and if you go with the next one, right? So t of, again further division. So 8 into 2t of n by 8 divided by 2 plus 2 plus 8 plus 4 plus 2. So which will be 16t n by 16 plus 8 plus 4 plus 2. So you can use a generic formula. So if it is 8, obviously we are getting, see, third division we are getting here like this. Okay, so this can be written as 2 power k of t n by 2 power k plus, so this can be written as 2 power k plus 2 power k minus 1 plus, and so on, plus 2. Okay, so if it is 4, it will be 2 power 4, and here it will be 2 power 4, 2 power 4, 2 power 3, 2 power 2, 2 power 1. So like this we can write it. And see from here, so when we are applying the stop condition, this is a stop condition. From here we can consider n is equal to 2 power k plus 1. Okay, so simply we can write it as 2 power k into 2, so which can be written as 2 power k plus 1, or simply we can write 2 power k is equal to n by 2. So remember these two formulas. Now what we have to do, so you can observe this particular pattern, which is a geometric progression, a formula of geometric progression. So geometric progression formula is, so a into r power n minus 1 by r minus 1, where a is a first term and r is the second term divided by first term, right? And if it is like 2 plus 2 square plus 2 cube plus and so on 2 power n. If the series is in this way, the formula will be a into r power n minus 1 by r minus 1. Just remember this one, right? So here a is the first term. So here a will be first term, that is a 2 into R is the second term by first term. What is the second term? 4. 4 by 2. Again it is 2. And here n. So here we are representing that as a k. Okay, here it is n, but here we are representing it as a k. So 2k minus 1 divided by 2 minus 1. So this can be considered in the place of this one. Okay, so hope you understood. So forget about this term, 2 power k into t of n by 2 power k. Right? So forget about this one. Just remember about this series. So this is like in the same way. 2 power 1, 2 power 2. So you can observe here 2 power 1, 2 square, 2 cube. 2 square, 2 cube, 2 power 4. So it will be keep on moving until 2 power k, right, from 2. So that will be in the form of this series. Now what we have done? We have applied the direct progression formula, a into r power n minus 1 by r minus 1, where a will be the first term and r will be the second term by first term. So it will be this one. Now apply the same thing in the place of this one. So I'll erase this one, right? So hope you understood. I'll erase these calculations. I'll apply the same thing here. So 2 power k into t of n by 2 power k plus, instead of this series we can write this one. So 2 into 2 power k minus 1 by 2 minus 1. So this can be written as 2 power k into t of n by 2 power k plus, it will be, so denominator will be 1, so it becomes 2 power k plus 1 minus 2. Okay, so 2 power k plus 1 minus 2. And here you can see so 2 power k t into, in the place of n we can write it as 2 power k plus 1. So 2 power k plus 1 divided by 2 power k plus 2 power k plus 1 minus 2. Okay, so I'll erase this one also. So what happens here? So 2 power k into t, what happens? This we can write it as 2 power k into 2 by 2 power k plus 2 power k plus 1 minus 2. So you can remove these two things. So now the formula will be 2 power k into t of 2 plus 2 power k plus 1 minus 2. Right? Now you can observe 2 power k. So what is the value of 2 power k? N by 2. So n divided by 2 into t of 2. That means we are having 2 elements. Okay, in the n we are having 2 elements. If it is 2 elements, see, if n is equal to 2, the result will be 1. Complexity will be 1. The comparisons will be 1. So we can simply substitute it as 1 plus 2 power k plus 1. 2 power k plus 1, it is n. So n minus 2. Okay. So from this we can write it as n by 2 plus n minus 2, which will be treated as 3n by 2 minus 2. So this is the number of comparisons we required in order to find the minimum and maximum elements using divide and conquer. So here also, if you observe, the worst case complexity will be order of n, because the highest degree is n. The complexity will be, here also the complexity will be order of n. Okay, in the linear model also, that the highest degree is n, the complexity will be order of n. Now you can check. So if you are having a 10 elements, okay, so we need to find the minimum and maximum from the 10 elements. If you apply the linear approach, how many comparisons will be required? So the comparisons will be 2n minus 2. That implies 2 into 10, 20 minus 2. 18 comparisons are required. 18 comparisons. And if you go with the divide and conquer, then the same comparisons will be 3n by 2 minus 2, which will be 30 divided by 2. Okay, 3 into 10, 30 divided by 2, 15 minus 2, 13 comparisons. So now you can observe, so if it is a linear approach, it requires 18 comparisons, and if you go with the divide and conquer, the comparison has been reduced to 13, which is an optimal solution. So you can feel the difference. So without using the divide and conquer, and after applying the divide and conquer, so obviously the number of comparisons will be reduced if you use a divide and conquer strategy. So final goal for every problem is to find the optimal solution in terms of complexity or time complexity or space complexity, whatever it may be. But the final goal is to get the optimal solutions. Now we can see clearly by using the divide and conquer method, we will be having the optimal solution. So it requires a minimum comparisons, less comparisons when compared to the conventional model or a linear approach, right? So hope you understood. So this is the stop condition. First we have to start dividing the complete problem into sub problems, and we have to continue the same process until the division results to 2 elements. So then we have to apply the algorithm, right? So let's stop here. Hope you understood and enjoyed, and if you are having any doubts regarding this process, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we will see one more application of divide and conquer method, that is a binary search. And in today's session we will see an example for the binary search, and then the algorithm, and finally we will see the time complexity, right? So today's concept is a binary search. So search means searching or finding an element, whether it is present in the given list of elements or not. So if it is there, automatically will return that element or a position, or we can say that element is found in the list. Otherwise we will say it is not found. And in order to solve this one, we are going to use this divide and conquer. That means we are going to divide the complete list into 2 halves, and we are going to solve the problem by selecting either one of the half, right? So every time we are going to reduce the search space. For example, if a list contains some 5 elements or 6 elements, in the second, after first iteration, after dividing the list, so then the search space will be reduced to around 3 elements or 2 elements. So like this, we are going to reduce the search space after every iteration until it gets only 1 element. Okay, so let us consider an example first. First, let us see the procedure, how we are going to solve that one, and then we will move on with the algorithm and then a time complexity. Now consider a list of elements, and one first thing very important, if you want to perform this binary search, make sure that the element should be in a sorted order. That is a one important constraint before starting this binary search procedure, right? So very important. So elements should be in sorted order. So this is important for binary search, and if you are moving with another one, linear search, so there will be no constraints. The elements can be of any order so that we can find the element, that we can perform the linear search. But coming to the binary search, make sure that the element should be in a sorted order before starting the binary search. Now consider an example. So we are going to take some sorted elements. So I will take it 10, 15, 35, 42, 58. So I'll take a small elements, okay, only 5 elements. So here I am considering 5 elements. So now consider this one as a low, this one as a high. Okay, low and high. First we need to find out the middle element. Okay, middle. So consider the index values 0, 1, 2, 3, 4, and this is the 5 elements. These are the 5 elements. And now we need to know the key value, that means the search key. So which element we are going to find. Let it be the search value is 10. Search value is 10. Now in the first step, find out the middle value. So mid is equal to, so low plus high divided by 2. So which gives, so 0 plus 4 divided by 2 is equal to 2. So middle is a 2. Okay, middle is 2. So what we have to check, see, the low is a starting element and high is the last element. Okay, low is the starting element, high is the last element. So always we know that low will be less than high. We know the process, right? So always low will be less than or equal to high, because if the elements are only one element, the same element will be pointing towards the low and high. So low is less than or equal to high. And if low is greater than high, then such is not possible. Or we can say that element is not found. Okay, if low is greater than high, then such will be not possible, right? So we need to repeat the same process. Okay, we need to repeat the middle, calculating the mid value until the low becomes greater than high. Now see, middle. Now what is the element of a middle, right? This one is a mid. Okay, so now compare the middle element with the search element. Compare middle element with the search element. So I need to compare search element, and let it be, the name of array is capital A. So A of mid. So we need to compare this one, right? So what happens, k is a 10 is equal to 35. Is it true or not? If it is true, that implies our search value is equal to the low of mid, A of mid. So obviously we can say that the element is found in the list. So if it is false, check 10 is less than 5 or 10 is greater than 5. First let us take the greater than, because it's a false condition. So 10 is a greater than 35. That means we are comparing the search with middle element. This is the middle element, right? So 10 is greater than 35. So it is false. Next, 10 is less than 35. So if you want to compare two values, only these three are possible. Whether either both are equal, either the first element is less than the second element, or either first element will be greater than the second element. Only the three possibilities. Now check, 10 is less than 35. Yes, this is true. What happens, that what says this one means search element is less than 35, and the constraint is elements should be in a sorted order, and from this point 10 is less than 35. Obviously that implies the search element may be less than the middle element, less than the portion of middle element. Okay, hope you understood. So here from low to high we are finding the middle value, and in the middle value we are checking and comparison. So we are comparing the middle element, and based upon this one we are selecting either we have to choose the left portion of the middle or right portion of the middle. And here 10 less than high, okay, 10 less than 35, it is true. Then we have to select the left portion, because all the elements which are less than 35 will be towards the left side of the elements. Now what we have to do? We have to change the search space, and here the search space is low to high, and now the search space will be low to, and already we have compared this middle element, right? Here we have compared the middle element. So the search space will be reduced to mid minus 1. Mid minus 1. Okay, mid minus 1. For example, if the search element, if the key is some 42, what happens? So up to this one, the same procedure. So 42 is equal to 35. Wrong. 42 greater than 35. True. That means whatever the element we are going to search, that is on right side portion because of this sorted order. So what happens? So the portion, the search space will be reduced towards the right side portion. What is the right side portion? Already the middle element has been compared. So we need to change the low value. So low value, so the search space will be mid plus 1 to high. Mid plus 1 to high. So we need to search only this portion. If it is less than this portion. Okay. So like this we have to repeat, and we have to check, and we have to stop this procedure whenever the low is greater than high. If the element is not found, automatically we will get the low greater than high. So then we have to stop this procedure. And see, so we are performing the division operation and one comparison. Division operation and one comparison. Right. See, we'll check. Now you can see 10 less than 35, then it is low to mid minus 1, and now the elements are so 10 and 15, and we should not consider 35. Mid minus 1 means here low 0, mid minus 1, 2 minus 1 is 1. So the search space is reduced to index values from 0 to 1, and here also 0 to 1, and you can see this one will be 0, this one will be 1, and we need to find out again a mid value. So this will be a low value, and repeat the same process which we have done is the same, right? So again calculate a mid is equal to low plus high divided by 2, which gives 0 plus 1 divided by 2 is equal to 0. So compare key value and 10, key value and A of mid. So which gives key value is 10, middle value at A of 0, that means A of 0 is 10. 10 is equal to 10. So obviously we found the element. If it is not found, again we have to repeat the same process. Again we have to repeat the same process. Okay, so hope you understood. So first the search space will be from low to high, and if after the first iteration, that means after finding the first middle element, we are based upon the middle element comparison, we are reducing the search space from either left portion or the right portion. If it is a left portion, the range will be from 0 to mid -1, and if it is the right portion, the range the search space will be from mid +1 to high, and we have to repeat the same process. Okay, now we'll write the algorithm. Recursive algorithm, right? We can write the recursive algorithm. So I'll write here. It's a very simple algorithm. Binary search. So we can take a lot of parameters, like array. We can pass the array, low, high, and key. So I will take it as some array, low, high, key. So we need to follow this order. First one is an array, second one is a low, third one is a high, and fourth one is a key. Now first we have to find whether low is less than or equal to high, and if it is low is greater than high, then simply we can say it is not possible. So if low greater than high, so we can simply return false. We can write return false or element not found, whatever it may be, based upon our logic, based upon our presentation, we can write it. And else, that means if low is not less than, low is not greater than high, next we have to find out the procedure. What we have to do? First we have to calculate the middle value. So middle value is equal to, so the same thing, low plus high divided by 2. So after getting the mid value, this is an index, right? Now we have to compare middle the key with the middle element. So here, if mid is equal to some array of, if key is equal to array of mid, then write down return true, or you can write it, yes, the element found at the position mid is the position, right? Else, again we have to check the condition, else if key is less than array of mid, what happens? If the search element is less than the middle element, obviously the search space will be left hand side. So what we have to do? On the left hand side means the search space will be reduced. So low will be remain same and high becomes mid -1. So you can write it the recursive call. So we can simply call the same thing. So binary search. What we have to do? So first one is array, low value is same, and the high value will be mid -1 and a key. Okay. Then else, if both the cases are false, that implies the key is greater than array of mid. So again we can write binary search, and now also array, the search space will be now reduced to right half. Right half means low value will be changed to mid +1. So mid +1 to high key. So this is a simple and very easy algorithm. So everything is, the complete problem will be divided, and based upon the division, based upon the comparison, we have to change the search space. Search space means from where to where, either low is changed or high is changed. So we have to repeat the same process until the low value is greater than high. So if this problem came low greater than high, that implies the element is not found in the array. Okay, so now we'll see the time complexity. Hope this is very simple. So hope you understood this one. Now we'll go with the time complexity. What is the time complexity? So the best case time complexity is order of 1, because if you are searching the search element is the middle element. For example, if key is equal to 35, how many comparisons you require? So here in this case, that will be the middle element. Obviously in the first comparison itself we will get the search. Okay, so it will be order of 1. It's a best case, and always we have to consider the worst case, right? So consider the worst case. So T of n is equal to, what we are doing? We are dividing and we are doing the comparison. So what we have to do? T of n divided by 2 plus 1. So we are not solving two portions. Okay, we are solving only one portion, either left half or right half. So that's why I am writing only one time, T of n by 2. And after that we are comparing, one comparison. And see, we need to find out the n, what is n, and see, in the first step we are finding n divided by 2. Okay, so in the next step we are finding n divided by 4. See, now we are checking n divided by 2, that becomes n divided by 4 plus 1 plus 1. And again we are performing the same thing in the next half. So n by 4 half, that means n by 8 plus 1 plus 1 plus 1. And similarly T of n by 16 plus 1 plus 1 plus 1 plus 1. So what happens? Every time we are dividing the search space into half. So first we are having some 5 elements. From that we are dividing the 5 to 2, and then we are dividing the 2 to 1. Okay, so we are keep on repeating the same process until we get the element, only one element. So you can simply say that this is T of n by 2 power k plus k terms. Okay, now when we have to stop, so that is also most important here, stop condition. So when we are going to stop this division, so n by 2 power k is equal to 1 element. So we are keep on repeatedly dividing the complete list, and we are stopping whenever n divided by 2k becomes 1 element. Okay, so from this equation we can say n is equal to 2 power k. So substitute the same thing here. So what happens here? So the same process will be repeated, and T of n by 2k is n plus, from this one, what is the k value? So log n base 2. So we can represent it as log n base 2. Okay, now what happens is equal to T of 1 plus log n base 2. So if there is only one element, then automatically it will be 1. So 1 plus log n base 2. So the time complexity, we can say the time complexity is equal to order of log n base 2. So this is the time complexity for binary search, okay, using divide and conquer. So here we are not combining all the solutions, so just we are dividing the complete problem into sub problems, and we are considering only one portion, not the two portions, and we are repeating the same process until it reaches to one element, and we are comparing, and if it is not found, we are saying that element is not available. So the only one constraint here is elements, all the elements should be in a sorted order. So that is the most important constraints we have to follow while starting this binary search process, right? So let's stop here, and hope you understood this binary search. We have seen the complete example with the small elements, and so try with the more number of elements, consider some 10 elements and try out with all the possibilities, left half, right half, and no element. Okay, so hope you understood and enjoyed, and if you are having any doubts regarding this binary search, so feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is merge sort using divide and conquer method. So the sorting is arranging the elements either in ascending order or descending order. So by default we'll go with the ascending order, right? That means a lower to higher. So one type of that process is a merge sort. So by using this merge sort also we can sort the elements, and this will follow the divide and conquer strategy, right? So we know about the divide and conquer, so it will be having some three stages. One is dividing the problem into sub problems, and second one is a conquer, so that means providing the solution or finding the solution for each sub problem recursively, and the last one will be the combine. So we need to combine the solutions of all the sub problems to get the main solution. So the same process will be applied for this particular merge sort, right? So here in this session we'll see, first we'll see an example so that we'll be getting an idea how the merge sort will be implemented, and then we'll go with the algorithm or a pseudocode. So based upon the procedure which we have known in this example, so we'll write the algorithm and we'll check, and finally we'll see what is the time complexity, the worst case time complexity of a merge sort, right? So we'll see one by one. So first let us start with the example. So let us take a few elements, unordered elements, and then we're going to use the divide and conquer method. So 50, 60, 10, 70, 30 and 40. So let us take these elements. Now we need, so we know that these elements are not in a sorted order, so we have to arrange them in the sorted order. So initially we'll write the index values 0, 1, 2, 3, 4 and 5, and we know, so this is the low, we will represent this one as a low and this one as a high, this one as a high. So the first step is divide. So we need to divide the complete problem into sub problems. So formula, so by which formula or by which criteria we need to divide the complete elements into two halves. So that is based upon the middle value, so mid value. So we need to calculate the mid. So mid is equal to, so low plus high divided by 2. So we need to consider only the integral part. So that will be low plus high by 2. That means 0 plus high 5 divided by 2. So which is 5 divided by 2, which is 2.5, and we need to consider only integer. So that will be 2. So mid is 2. Mid value is 2. So here I write mid is equal to 2. Now what happens? We need to divide the complete problem into two halves based upon this mid. Okay, so what's the mid value? 2. So this is a mid. Okay, so where we have to divide? So one part is from low to mid, and the second part is from mid plus 1 to high. So based upon this one, we need to divide the complete elements into two halves. So here we will write, so 50, 60, 10, 70, 30, 40. So this is one part, and this will be the another part. So again we need to divide the elements further based upon the middle. So we have to solve these two parts individually and recursively. So what happens here? This is 0, 1 and 2, and we need to calculate the mid. Mid is equal to 0 plus 2 by 2. 0 plus 2 by 2. So which will be 1. Which will be 1, right? So we need to divide this one into two halves. So 50 and 60. That means low and mid plus 1 and mid plus 1, right? So here also we need to apply the same process. So mid is equal to 0 plus 1, sorry, 0 plus 2 by 2, so which is 1, right? So this is 1, 2. So now here also the same process. It was divided into 70 and 30 and again 40. So two parts. So complete data is divided into two parts, and each part is again further divided into two parts. And similarly here also it is 0, 1 and it is 0, 0, 1 and it is 0. So here again we need to divide. So mid is equal to 0 plus 1 by 2, which is equal to 0. So we need to consider 50, we need to consider 60, and here is only one part, that is 10, and here also the same. So mid is equal to 0 plus 1 by 2, because this is a L, this is a high, low and high, low and high. So low plus high by 2. So here also we need to use the same thing. So 70, 30, 40. So right, this is the process. This is the process. Right? This is the process. Now we got a complete elements here. Now what we have to do? We have to compare each and every element, and we need to arrange the elements in a sorted order. What we have to do? So we need to compare this 50 and 60. Okay. So 50 and 60, obviously both are in the same, right? And this is 10, and apply the same process here also. So 30 is greater than 70, so 30 is less than 70. So we can see 30 and 70 both comes in the same thing, and now it will be the 40. See what we have to do. So let us assume this one as I, and this one as J, and this one as I, this one as J. So we need to compare I and J. Here also you can see this is I and this is J. This is I and this is J. So we need to compare the I value and a J value, and if the element whichever it is lower, that should be loaded in the new array. So this is the new array. You can observe this is a new array, right? So compare 50 and 10. Which is the highest? So which is the lowest? 10. So obviously 10 will be placed here first, and this value will be incremented. That means it will be moved to the next one, next element. And here also, now there is no element in J. If in such cases, whatever the elements remaining in this particular subarray, so that will be loaded into the new array. So 50 and 60. See, 50 and 60. So after combining this one, so we got these elements. Similarly, here also, let us assume the new array. See, 30 is compared with 40. So, which is lower? 30. So, 30 will be stored in new array, 30. And immediately, I value will be incremented. So, now I value is pointing towards 70. Again, repeat the same process. 70 and 40. So, 40 is a lower. So, now place 40 here and j is incremented. So there is no other value in this particular array. So whatever the elements remaining in this sub array, that will be loaded into the new one. So 70 will be copied here. So you can observe after every step we are getting the elements in a sorted order. So here you can see 10, 50, 60. These elements are in sorted order. 30, 40, 70. These elements are in sorted order. Now what we have to do? So we have to combine these two arrays. So after first division, you can see 50, 60, 10. And now it is 10, 50, 60. After division 70, 30, 40, here you can see 30, 40, 70. So we have to compare each and every element of both the arrays. And we have to create a new array. And if whatever the element which is lesser, that element should be copied into the new array. And that index should be incremented towards next one. So if there is no other element in the array, then automatically whatever the elements remain in the next array or the another array should be copied into this one. Now, if you are still having any doubts, so let us solve this one so that you will be understanding, right? So here we are having 3 elements and here we are having 3 elements. Now we will solve this one. So I will erase this one. Right. So let us consider 10, 50, 60. So 3 elements, and here also we are having 3 elements, 30, 40 and 70. See, now what we have to do? So we have to compare each and every element, right? See, so let us consider this as I, this as j. Okay, this as I and this as j. Now, what we have to do? So we have to compare 10 and 30. We have to compare 10 and 30. So this is a new array. Okay, this is a new array. So 10 and 30. So which one is less? 10 is less. So obviously 10 will be stored in the new array. So 10 will be stored in new array and I will be incremented to the next one. Because 10 is already here, right? So I will be incremented to the next one. J remains same. Okay, J remains same. Now 50 is compared with 30. So which one is low? 30. So 30 will be copied into the new array. Right? 30 will be copied to the new array. Now J will be incremented. J will be incremented. Again compare 50 and 40. Which one is low? 40. So 40 will be stored here and again J will be incremented towards here. And again 50 and 70. So 50 is less. So 50 will be copied here and I will be incremented towards here. So 60 and 70. 60 is less. So 60 will be copied here and I will be incremented and there is no element in the array. So it goes beyond the index. So then immediately what we have to do? So we have to go with the next another array. And whatever the elements remaining in that array will be directly copied to the new array. So only one element is there. So already 10 we have copied, then 30 is copied, then 40 is copied, 50 is copied, 60 is copied. So only one element is remains here. So we will simply write 70 in this place. Okay. Now we have taken the elements here, 6 elements, 50, 60, 10, 70, 30, 40, and now we are getting the elements in a sorted order. So 10, 30, 40, 50, 60 and 70, right? So here we have done the division. So where we have divided the complete problem into 2 halves based on middle value and then conquer. So recursively we are keep on solving by comparisons and then combine. So we are merging merging or combining all the different subproblems so that we are getting the final solution, right? So hope you understood this one. So based upon this explanation, we will write the algorithm, right? Yes. So what we have to do, we have to divide the complete elements into two different halves. So let us write merge sort. Okay, merge sort. So here we can write yes, one is array, another one is low, and another one is high. Okay, now what we have to do, so if low is equal to high, that means only one element, right? There is no comparison. Okay, there is no comparison, nothing can be done, so we can return a direct elements, return element. Okay, so only one element means that will be in the sorted order. Else what we have to do, we have to divide. So recursive call, again apply the merge sort, and what we have to divide, so array of elements and then low to mid, and then again we have to divide merge sort a mid plus 1 to high. So once the division has been completed, then we have to combine. So that we call it as merge. So don't get confused. Merge sort is different, merge is different. Merge function. So here we will write low, high, mid. Okay. So what we are doing? So first we are checking whether it contains a multiple elements or a single element. If it is single element, simply we can return the element. And if it is a multiple elements, then we have to divide the multiple elements into two parts. One is from low to mid and mid plus 1 to high. And once it was completed recursively, then we have to start merging both, all the solutions, right? So we'll write the merge part here. Merge three things, that is low, high, mid. Okay, also we can take array because we need to pass the array, so also we can write array. Four parameters, array of elements, low, mid and high. Now, okay, so what we have to do, so we have to check, so we have to initialize first, let us initialize I is equal to low and j is equal to what we are doing. So we are taking two parts, and here I am writing I and here I am writing j. So right, so I is a low, j will be the first element of the second array, so which is nothing but mid plus 1. Hope you understood, right? So j will be the first element of second array, I will be the first element of first array, so automatically I will be low, that is 0, and j will be mid plus 1. And we need to continue this process until the two conditions satisfies, I less than or equal to low and j less than or equal to high. So here, here it is not low, it is mid, because so until I reaches mid and here until j reaches high, because this position is mid and this position is high. So we are keep on comparing each and every element and we are incrementing the I value and j value, and this process should be repeated until I reaches to mid or j reaches to high. So I less than or equal to mid and j less than or equal to high, we have to repeat it. What we are doing, we are comparing this element and this element. So what is the element? So comparison means a condition, right? So if a of I less than a of j, what we are doing? So if a is less than, this element is less than this element, what we are doing? We are copying this element to a new array. Let us consider here a new array. Some b is equal to, okay, so let us take index value 0. B is equal to index value 0 and b is some array of multiple size. Let us take some 10 array. Okay, so what we have to do? So b of I plus plus, sorry, so here we have taken b is an array and let us take the index value as 0. So b of k plus plus is equal to a of I plus plus. So what happens? This is the postfix. Okay, postfix. First it will be copied and then automatically it will be incremented. And you can also write the same thing in this way. B of k is equal to a of I, and you have to increment the I value. So once you copied this element into this one, we have to increment the I value, right? So we have incremented the I value. And simply you can write else what happens? If it is false, that implies a of j is less than a of I. So a of j should be copied here. So this element should be copied here. So b of k is equal to a of j, and j should be incremented. J should be incremented. So j should be incremented to the next. And both the cases we have to increment the k plus plus, because once the element is inserted here, the k should be incremented so that the k points towards here. So k should be incremented, right? So once all this done, then if it reaches to here, what happens? We have to move all the elements of first array to the new array, or all the elements of second array to the new array. So for that we can simply write a loops. So while, simply write it I less than or equal to mid. Okay, I less than or equal to mid. Simply write down b of k is equal to a of I, and simply write one more thing, j is equal to j less than or equal to mid. B of k is equal to a of j. See, this will be happened. Okay, this will be happened. Sorry, here you have to close, and this is outside the loop. Outside the loop. Okay, so what we are doing? We are comparing the elements, and we are selecting the lowest element, and that element will be copied to the first position here, and then we are incrementing the I value. So the same thing happens here. This code is the similar, right? So once I reaches to mid, what happens? So we need to check whether the elements are remaining in the either of the array. So if they are remaining, so we need to copy all the elements to new array. Okay, and here also we need to increment the k value and the I value. So in both the cases, I value and k value will be incremented. So simply we can write it as k plus plus I plus plus. So because of this post increment, first the value will be copied and then the this one will be incremented. Okay, so this is a algorithm or a pseudo code, so whatever it may be. So based upon our explanation on an example, right? So hope you understood this one. Now we'll move on to the time complexity. So what is the time complexity of this merge sort, right? So we'll see what is the time complexity. So what we are doing, so time complexity of 1, if it is one element, that will be 1, right? So T of n is equal to, so first the problem is divided into two parts and we are solving both the parts. So T of n by 2 plus T of n by 2. So two halves, and we are considering both the things because we are solving both the parts. Okay, whereas coming to the binary search, so we are moving on with only one part, right? So that's why we have not included both the parts, right? But here, so we need to solve both the arrays. We are dividing the problem into different parts, and we have to solve all the parts. So we have to consider this one, and plus what we are doing? We are doing n comparisons. So how many elements are there? Then that many comparisons we are doing. So we are comparing each and every element and we are performing the operations. So plus n. So this we can write it as 2t of n by 2 plus n. Okay. Then coming to the relation. So if n is equal to n by 2, right? Then t of n by 2 is equal to 2 into, okay, t of n by 2, right? So 2t of n by 2 divided by 2 plus n plus n. So it will be 4t of n by 4 plus, so what happens here? So this is n by 2, right? So 2 into n by 2, it will be n plus n. So which gives a 4t of n by 4 plus 2n. Okay. So the same thing, right? Plus n means here we are in the place of n we are dividing the n by 2. So once again in the further process, right? So first there are some 6 elements, then 3 elements. Again 3 is divided into 2 parts. Further division, so we can write 4 into 2t of n by 2 divided by 4 plus, okay, n by 4 plus 2n. So it will be 8t n by 8 plus n plus 2n, which will be 8t n by 8 plus 3n. So this will be keeps on moving, right? This will be keeps on going. So that can be written as 2 cube. 8 can be written as 2 cube t of n by 2 cube plus 3n. So this can be written as t of n is equal to 2 power k t of n by 2 power k plus k into n. So this process will be repeated. So what is the stop condition here? So when we are going to stop the division, right? So here I'll write stop condition. So this is the most important, right, while calculating the time complexity. So whenever it will be, so we are keep on dividing the problem and we'll stop when it becomes one element. When it becomes one element. So obviously we can write it as k is equal, n is equal to 2 power k and k is equal to log n base 2. So this is a stop condition. Now you can know, so k value you know and 2 power k value you know. So substitute the same thing here. So 2 power k, which is nothing but n into t of, okay, n into t of n, it's a 2 power k, or simply we can write n by n plus, what is the value of k? Log n. So log n base 2 into n. So this will be n into t of 1 plus n into log n base 2. And this becomes 1. So that will be n plus n log n base 2. And obviously you can see the highest degree, that is n into log n base 2. So the time complexity, the worst case or average case time complexity for the method will be n into log n. That means we have to write by using the asymptotic notation. So big O of n log n. So this is the time complexity for merge sort. This will be the time complexity of merge sort, right? So hope you understood the time complexity for this merge sort. So whatever the process we have studied right now, so we have seen one example, and after knowing the example we have written the pseudocode and then we have calculated the time complexity for this merge sort, right? So hope you enjoyed the session. So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.
Hello friends, welcome back to our channel. Today's session we will go with another sorting mechanism that is called a quick sort. So this sorting mechanism will follow the divide and conquer method. Divide and conquer. So the name itself indicates. So divide and conquer means first the complex problem is divided into subproblems, and each subproblem will be implemented. So like that, here also the complete large elements will be divided into different partitions, and each partition will be applied for sorting technique. So each partition will be implemented by using the recursive methods. Okay. Next, so let us see the procedure first, and then we'll go with the example. Then first step, here we have to select the pivot, and we have to find the position of the pivot element. So here we will go with the pivot element, right? So first we have to find the position of a pivot. Position of a pivot such that all the elements which are left towards this pivot are less than the pivot element, and whatever the elements which are on the right side to this position are greater than a pivot, right? So this position, first we have to find this position, then consider this as one partition, consider this as another partition. So see, this is less than pivot, this is a greater than pivot, don't get confused. Okay, this is a less than symbol and a greater than symbol. Okay, so less than pivot is one partition, greater than pivot is another partition. So recursively call the same procedure for this partition. Again consider a pivot and find the position of the pivot for this partition, and again divide that into two positions, right? So like this we have to find this quick sort. First, this pivot can be considered as the pivot element can be considered as first element, middle element, last element, right? So we can consider any element as a pivot element, and based upon that pivot element we have to find the position of that particular pivot element, right? For example, if the numbers are 50, 40, 10, 30 and 20, this element can be considered as a pivot, or this element can be considered as a pivot, or this element can be considered as a pivot. So after considering the element as a pivot, we have to find the position of that particular pivot point such that all the elements which are less than pivot should be on the left hand side, and all the elements which are greater than the pivot should be arranged on right hand side. So in such a way we have to find the position of the pivot. First we have to consider the pivot element. What is the pivot element, right? So in our example we will consider this one, first one. So let us consider the first element as a pivot and find the pivot position. See, first consider first element as a pivot. Consider the first element as a pivot Next, initialize I to low index, j to high index. That means the starting element, j is the last element. Next, we have to repeat the procedure. Repeat the following steps. Until I less than j. So until I becomes until I less than j, until the condition is true, we have to repeat the following procedure. So first, keep on incrementing I while a of I is less than or equal to pivot. So unless this condition becomes false, we have to keep on incrementing the I value. Right. Next, similarly, keep on decrementing the j while a of j is greater than pivot. So similarly, from the starting, we have to incrementing the I towards the right, and we have to decrementing the j towards the left. Okay. So while incrementing and decrementing I and j values, we have to check these conditions, whether a of I is less than or equal to pivot, and whether the a of j is greater than pivot. Right. Next, so if this two condition fails, if these two at some condition, this condition, I mean at some point this condition will be failed, so we have to stop incrementing the I. At some element, this condition will be false, so we have to stop decrementing the j. Now check the condition. If I is less than j, yes, then if it is true, then swap the elements a of I, comma a of j, a of I, comma a of j. So we have to swap the elements of I value, the elements which are available in ith index and jth index. Next, if this becomes false, I less than j. So if I is greater than j, the index value of I is greater than j, then also we have to swap a of j element with the pivot. So this is nothing but, this is nothing but a of low, because here the pivot is the first element, right? Pivot is the first element. So we have to change the swap between the jth element and pivot value. So here j is the position of pivot. So this is very important thing, right? J is the position of a pivot, so that all the elements which are less than pivot are on the left hand side, and all the elements which are greater than the pivot will be on right hand side. So here, after completion of this one, the pivot value will be fixed. The pivot position is fixed, right? Not the pivot value, pivot position will be fixed, right? So we are supposed to find that position of a pivot. Now divide the two partitions. So one is some after getting the pivot value, right? So this is one partition and this is another partition. So this is 0 to p minus 1 and here p to high, p plus 1 to high. Okay, p plus 1 to high. Instead of writing 0, we will write a low. Right. Low to p minus 1. So this is one partition, this is another partition. So consider this partition and here also consider repeat the same process. So recursively repeat the same process. Consider this partition as a array of elements. Now consider the pivot, first element as a pivot and starting I to low index and j to high index. So I will be low, j will be p minus 1. And then repeat the following steps until I less than j. So keep on incrementing I while ia of I is less than or equal to pivot. And then keep on decrementing the j while a of j is greater than pivot. Right. Then if I is less than j, the index values of I is less than j, then simply swap the positions of I and j, the elements which are at positions of I and j. Then if I is greater than j, the index value of I is greater than the index value of j, then simply swap the low value with the a of j. That means of the value present at the position j. So here a of low means nothing but a pivot value, because in the first step we are considering the first element as a pivot. So here again the pivot, the position j is the position of pivot. So position, when the pivot position is fixed, so that all the elements of which are less than pivot will be on left hand side, and all the elements which are greater than pivot are available in the right hand side. And again do the partitions and again repeat the same process. Right. So this is how we will implement. We are going to implement this quicksort. Right. So based upon this algorithm, let us solve an example so that your doubts will be clarified. So our aim is to find the position of a pivot, and we will implement the same thing recursively for all the partitions. So once the pivot is fixed, then we have to divide it into partitions and considering each partition, and we have to repeat the same. Okay. Example. Let us take some elements. Consider these elements. Okay. See. So these are the elements of an array. So this is array elements. These are the indexes. This is the I value. This is the j value. I value, j value. Okay, right. Then consider this as a pivot. Consider this element as a pivot. Now repeat the process. So first step, consider the pivot as a first element. So we have considered this one, and next I is initialized to low and j is initialized to high. So I less than j, that is here 0 less than 5. The condition is true. So this condition is true. We have to repeat the process. So what we have to repeat? We have to keep on incrementing I until a of I is less than or equal to pivot. So a of I less than or equal to pivot. See this condition I plus plus. We have to repeat the same process. Okay. So here see first 30 less than or equal to 30. So I plus plus. So that means 1 it will be. Next 20 less than or equal to 30, I plus plus 2, right? Next, 10 less than or equal to 30, I plus plus 3, index value 3. So 50 less than or equal to 30. So fails. Okay, fail. Here the fail condition fails. Now here at what condition it is failing? I is equal to 3. So I is equal to 3. Right? Condition I is equal to 3 fails. So after completion of this one, I is pointing at here. Okay. Now keep on decrementing the j value. So a of j is greater than pivot if I j minus minus. So repeat this process. So a of j is nothing but a high value, high value 5. So 40 greater than or equal to greater than 30, j minus minus. So it will be 4. Next, 60 greater than 30, j minus minus. It's again 3. After decrementing, it will be 3. Next, 50 greater than 30, again j minus minus 2. Next, 10 greater than 30 fails. So at where it fails, j is equal to 2, right? So at some condition, at some element, both the condition will be fails. Now we have to check whether I is less than or j. So what is the, see, if I less than j, then swap a of I element with a of j element, right? Else we have to change, swap a of j element with pivot, right? Now let us check the condition here. So I less than j, so 3 less than 2, I less than j, 3 less than 2, which is false, right? So we have to swap a of j. A of j means, say j is 2, a of 2 comma pivot. What is the pivot? 30, or a of low, okay, a of 0, because here the pivot is a of 0, right? So swapping j position is pivot. So what is the j position? 2. Second position is a pivot element. Second position is the pivot element for the first thing. So after getting this one, see, just swap the positions a of 2 comma a of 0. A of 2 means 10. So 10 will be here, 20, then 30, then 50, 60 and a 40. See, 0, 1, 2, 3, 4 and 5. So second position is a pivot. Second position is a pivot, right? So here if you observe, all the elements which are on the left hand side of the pivot are less than this pivot, 10 and 20. So it may be in a sorted order, or it may not be in a sorted order, right? So whatever the elements which are on the right hand side of the pivot are greater than the pivot elements, right? So this may be in a sorted order and this may not be in a sorted order. So this is the partition 1, this is the partition 2, right? So now we have to consider, so this position is fixed, right? Pivot position is fixed. So we have to take care about the partition 1 and partition 2, excluding this pivot position. So that's why we are writing from 0 to low to p minus 1, and here p plus 1 to high. So we are not considering the pivot position because it's already fixed. So hope you understood this one. So after the first iteration, first recursion, this is the elements. Now let us write these elements. Okay. I will write down here. So 10, 20, 30, 50, 60 and 40. Right. So I will erase all these things. So first recursion. This is about the first recursion. Now. So this is the pivot element, okay, fixed. So this will be the partition 1 and this will be the partition 2, right? So let us consider these partitions. So 10 and 20, 0th index, first index. So obviously this will be I, this will be J, and also pivot. We know that we are considering the pivot as a first element, so this one. So what we have to check? We have to repeat until I is less than J. Here it is 0 less than 1, condition true. Then keep on incrementing. So A of I is less than or equal to pivot I plus plus. So for this we have to go with this. So 10 less than or equal to 10, I plus plus, that will be 1, and a 20 less than or equal to 10, okay, so false. So I is equal to 1, oh sorry, right, I is equal to 1. So I value is changed from here to here, okay. Next, A of J greater than pivot, we have to keep on decrementing the J value. We have to keep on decrementing the J value. So 20 is greater than or equal 20 is greater than 10, J minus minus, right? J minus minus, and the value will be 0 now because initially J is equal to 1, and 10 is greater than 20, which is a false. So J is equal to 0. See, at I is equal to 1, the condition fails. At J is equal to 0, condition fails. Here, if you observe, I is less than J, then what we have to do? Swap A of I comma A of J. Else, oh sorry, we can write the condition, okay, I greater than J, then swap A of J comma pivot, right? Pivot, right? So here we can observe here at what positions the condition fails. I is equal to 1 and J is equal to 0. So 1 less than 0, the condition is false. So this will be happened. So swap A of J means 0 comma pivot. Here pivot means again A of 0. So that implies so both the J position, both the J value and a pivot are at the same position, so we need not swap anything, right? So already those are in sorted order. That means these are in a sorted order because we need not swap any element. Okay, only two elements are there. We need not swap any element. So this will be the pivot position. Okay, so here see, J position is a pivot position, isn't it? Right. What is the J position? 0. So 0th is a pivot position. If 0th is a pivot position, see, left hand side we are not having any elements. Right hand side we are having only one element which is also greater than 10. So it implies this partition is already in sorted order, right? Next, hope you understood. Next, we will go with the partition 2. We will go with the partition 2. So this is already in sorted order. Now, we will repeat the same process with the partition 2. So 50, 60 and 40. So 0, 1 and 2. So this is the I value, this is the j value. Okay, this is the I value, this is the j value, and this is the pivot. Right. So continue the process. So I less than j, that is 0 less than 2. So this condition true. Then a of I less than or equal to pivot I plus plus. So keep on doing all these things. So a of I, that means a 50 less than or equal to 50 I plus plus, that means I becomes 1, initially 0. Next, 60 less than or equal to 50 fail at I is equal to 1. At I is equal to 1 it fails. So now I becomes here. Then similarly a of j is greater than pivot j minus minus. So repeat this process. So j value is a 40, 40 greater than a 50, 40 greater than 50. Condition false. So at j is equal to 0 position. At j, at j is equal to 2. At j is equal to 2, the condition fails. Okay. Then see, if you observe here, check the condition I greater than j. Here I is 1 greater than 2. I greater than j. It is a false. So swap. I'm extremely sorry. I less than j. So if I is less than j, we have to swap the elements a of I and a of j. If I is greater than j, then we have to swap the elements a of j and pivot. So here the first condition, I is less than j. I value is 1, j value is 2. So I is less than j. So swap a of I comma a of j. So what are the elements we have to swap? Swap the 60 and 40. So the elements will be, after the iteration, the elements will be 50, 40, 60. 50, 40, 60. The positions of I and j are same. Okay. So the index values 0, 1 and 2, and this is the pivot we are considering. Right. So after swapping 60 and 40, we will get this one. Okay. Now again repeat the same process. So a of I is less than or equal to pivot. So I plus plus, consider this one. A of I, that means a 40 less than or equal to 50 I plus plus, which becomes 2. Similarly 60 less than or equal to 50 fail at I is equal to 2. Right? At I is equal to 2 it fails. Now I and j are positioning at the same point. I and j are positioning at the same point. Similarly a of j is greater than pivot, then simply decrement the j. Repeat the process. So 60 greater than or equal to 50, not equal, greater than 50, j minus minus, which becomes 1. Similarly 40 greater than 50, which fails at position j is equal to 1. Now j is positioned at 1. Right? Now check the condition. So if I is less than j, then swap a of I comma a of j. Just a minute. Else swap a of j comma pivot. Right. Now here I is 2, j is 1, 2 less than 1, false. So we have to swap, false condition, swap a of j comma pivot, which is nothing but swap a of j means a of 1 40 comma a of pivot 50, and we know that j is pivot. J is pivot, that means 1 is pivot here. Okay, so here 1 is pivot. So after completion of this, okay, after completion of this, so I will erase this one. Okay, right. So here j is a pivot. J is pivot. Here what is the value of j? 1. So 1 is a pivot position. 1 is pivot position. So we have to swap. After swapping 40 comma 50, the elements are 40, 50 and 60. The positions 0, 1, 2, the position, this is the pivot position. So left hand side of the pivot is having the values less than pivot, and the right side of the pivot position are having the elements greater than pivot. So here again this is the one partition, this is the another partition. So here the partition is having only one value, so need not apply the sorting technique, and here also the partition is having only one value. Here also we need not apply the sorting technique. So finally, after completion of all these things, we can simply have (40, 50 and 60). Okay, so this is a procedure we are supposed to apply. So hope you all you understood this one, right? After the first iteration, 2 is a pivot, so that 2 partitions are there. First partition, again 0 is the pivot. Second partition, 1 is a pivot. 1 means the position 1, index 1. Okay, index 0 and index 1. Right? So hope you understood this one, the quicksort algorithm, how it apply for this, how we are dividing the complete elements into different partitions, and how we are applying the recursive functions. Right? So simple thing. So first we have to consider the pivot element, and first to find out the position of that particular pivot element, and then based upon that particular pivot element we have to divide it into the partitions and recursively apply the same procedure.